Okay, hi everyone. My name's Thomas Dixon, and I'm presenting here a bit of a summary of an experiment that we've been working on for the past year. It's called Stroboscopic Detection of Multi-colloidal Hydrodynamics using time-multiplexed optical tweezers. So it's a bit of a mouthful, but the kind of idea is that we're using time-multiplexed optical tweezers, and we're trying to do some interesting hydrodynamic experiments. So a quick summary, if you just kind of want to take a look and see if this is worth your time. We developed an interesting, in my opinion interesting, time-sharing optical trap that uses a field programmable gate array, or FPGA, that kind of combines the control of holographic optical trapping, where you can specify a number of different positions for your optical trap, but also with the data rate of photodiode-based sensing. And then to prove that it works and to prove that it's analogous to continuous power systems, we replicated a bunch of continuous power experiments and did some other stuff as well to kind of show that this method will work for a variety of different cases, both passive cases where you've got, say, spheres just chilling out, or, sorry, colloids just chilling out next to each other, or for dynamic systems where we're driving one or more objects and kind of looking at the response of the system as a whole. And it turns out this is a very similar method to another method that was published in May of this year, so after we submitted this abstract, but before this conference. So that's good for you. There's going to be 2 papers out kind of talking about a similar method, so I really do encourage reading that paper down the bottom and, of course, checking out our conference paper at the end of this presentation. So the kind of justification as to why we were doing something like this was that we wanted to explore the hydrodynamics of multi-colloidal systems because it's a really useful application for optical tweezers. But holographic optical tweezing, which is where you're using say a spatial light modulator or a deformable mirror or a micro mirror array, really isn't compatible with photodiode sensing, because it's essentially when you've got multiple beams being created from your holographic optical trap, they're going to smash on top of each other if you're going to be trying to use photodiode-based interferometry, which in our case we're using back focal plane interferometry, or BFPI. And we thought, well, as long as it's quick enough, time sharing of a single laser between multiple positions should be roughly analogous to a continuous power trap. So if the switching is quick enough such that the Brownian motion of the particle isn't really that large, then this should function quite similarly to a continuous power trap, albeit at a reduced power. So if we have 2 simultaneous traps, one after the other, then that should function like 2 half-power traps compared to our continuous case, and so on. So in this presentation, I'm going to walk you through our development of a dynamic time-sharing solution. So we're actively controlling where the positions are, and you can change them dynamically, that retains photodiode sensing capabilities and can work for passive and active hydrodynamic experiments, so for static and driven systems. Now the setup is a little complicated, but it is mostly just an FPGA does everything. So over here, and I'll see if I can get a laser pointer. Excellent. Over here is our FPGA, our field programmable gate array. We're using a LabVIEW one. You can find the details in our conference paper. That is effectively doing all of the time multiplexing. You can send up to 1,000 trap positions to this FPGA, and what it does is it interfaces with a 2-dimensional acousto-optic deflector. Effectively, it's setting the amplitude and frequency of an acoustic wave that changes the deflection position of our laser. Now, what essentially it does is it cycles through all of the positions you give it. So in this example, I've given it 3 positions. You can also specify the time in between each position, which is going to come in handy a little bit later. But effectively, our 2D AOD is cycling between, in this case, 3 different positions. And so the laser is on one trap, then it's on another one, and then it's on a third one. And this has kind of already been done before. Time division multiplexing with AODs is a fairly common methodology, but where ours is kind of interesting is we're also using this FPGA to handle our data. So we are using your conventional back focal plane interferometry, so we've got our 2D AOD, laser shoots through that, shoots off an SLM, which is just for aberration correction, not for anything else. We're not using it for actually any holographic optical tweezing. Shoots through some optics, goes into our sample, and then the scattered light comes out and hits our position-sensitive diode. Now, this diode is going to be gathering data all the time, even when the system is switching, and a lot of that data is kind of useless, and it's quite difficult without an FPGA to synchronize the trap position and the data being gathered at any one time. But because the FPGA is a really, really fast piece of hardware, we are able to kind of extract the useful data from every single switch. So it's keeping track of what the trap position is, it is keeping track of how long since the trap position has been switched, and after a switch delay time, which we'll talk about a little bit later, of around 60 microseconds, so this is kind of the dead time when the trap is still switching to its new position, it gathers some useful data. And then the FPGA outputs it to our computer, and then we essentially do regular analysis that you would expect from a hydrodynamics experiment. Now, this system is quite robust and useful for a bunch of different experiments, but the first thing they want to talk about is that we can use this originally to actually do calibration. So one of the things that's kind of important if you want to do good position measurement is to calibrate the response of your detector to a specific position deviation in your system. So especially so if you've got multiple traps or multiple particles around and you worry that, say, the scattered light off of one particle might affect the measurement of another particle. So in order to do this, what we've done is, because you can send any arbitrary configuration of traps into our system, we are taking a single trap, deviating it by a known distance, and waiting for a sufficient time such that the particle definitely stays there, switching the trap back really quickly and gathering data at this particular configuration, which will tell us what the exact position signal is going to be for a particular deviation, and then cycle through the other traps just to make sure that the particles don't deviate, and essentially to make sure they maintain there. Now, this allows us to handle multiple different shapes of particles and particles that are in weird configurations, because we're not really worried about our BFPI signal, or our back focal plane interferometry signal, being distorted by any of the particles that are around our target particle that we're measuring at that time. And of course, this repeats for every other particle in the system. So sometimes it takes a while, but the system that we've made is quite robust. As long as you just specify the trap positions, it'll kind of handle all of the rest of it itself. One other thing that we can do, instead of just having particles adjacent to each other, is we can do arbitrary control of the trap position. So in this case, I'm going to be talking about sinusoidally driving one particle whilst having the other one stationary. Now, this is pretty easy because all we need to do is interleave two different traps, right? So it goes to this position, then it goes to that position, then it goes to this position, goes to that position, etc. But every second position is deviated somewhat. And if you add up all those deviations, it matches a sinusoid. And this is a quite interesting phenomena that we can kind of exploit. We're going to be doing some dynamic interaction experiments a little bit later. But one thing to note is that because our system is time limited by our switch rate, here I've assumed 100 microseconds, which I'll talk about a little later as to what the actual maximum possible switch rate is. But because we're limited by the switch rate, we actually have a bit of an annoying discretization error for our sinusoid. So depending on the number of traps that you want to have simultaneously, you are going to run out of nice positions to have your sinusoid. So it's going to start to approximate a triangle wave. And at that stage, one can't really assume that it behaves like a sinusoid. So high-frequency systems are limited by discretization error here. So for example, if you wanted 4 traps all sinusoidally oscillating, you're going to get limited by around 300 Hertz in our system. And this could be improved, of course, by improving the switch rate, which we'll talk about a little bit later. Now, our low frequencies, so how long the maximum period of a sinusoid can be, is actually just limited by the memory of our FPGA. So we can put in 1,000 trap positions, and that effectively means that you have 1,000 positions in order to make a complete sinusoid, a complete cycle, because it just does cycle through those up to 1,000 positions. And so again, you could extend the switch rate out, and that would extend the frequencies available, but there is an unfortunate relationship between the switch rate and the data rate, which I'll talk about a little bit later. So let's talk about the performance of the system, and then I will talk about some of the experiments that we did to validate it. The temporal resolution is around 75 microseconds. So when I say it's around 75 microseconds, the sensing that we're doing for our position-sensitive diode is on the order of 5 microseconds or lower. We're able to interrogate the diode much quicker than that. But when you are taking a position measurement, there is a lot of time that the measurement is not really useful. When the particle has just switched from one position to another, or sorry, when the trap has just switched from one position to another, the data there is not really useful. And to check this out, we actually just put a really fast photodiode in our system, just right at the front, and switched it at a bunch of different speeds to see how long it took for the trap to kind of get into its nominal position. Now, I put around 75 microseconds to 100 microseconds as our approximate temporal resolution, and that is essentially the fastest that you can be driving the trap. Because, unfortunately, you only get data after the switch. So, data points are going to have to be once every 75, once every 60 microseconds, considering it's got to swap to a certain trap position, wait for it to settle, and then you get to take a data point. Now, the spatial resolution is just like what you'd expect for photodiode sensing. So it's typically 5 nanometers, depending on the size of the particle you're using, depending on the power, the trap power, depending on how well aligned your system is. But for our systems where we're doing 1 micron spheres, the spatial resolution is, well, technically it should be better than 5 nanometers, but we're going 5 nanometers just to be conservative. Now, technically, although you can specify 1,000 traps to our system, the number of simultaneous traps that you can effectively have is limited by the data rate. So if you have 13 simultaneous traps, it's like 13 different positions in whatever array you want, then each trap is only going to be hit once every millisecond. And so that's really going to limit the effective number of simultaneous traps. We're never going to get 1,000 simultaneous traps, because that's going to be a very long time between the laser being in one position and cycling all the way back to hit it again. They're all just drift out of the trap. And as I said before, depending on the switch rate that you've got for our sinusoids, we can oscillate things between 10 and 600 Hertz. Now, these data numbers are okay. The best thing that could be improved is our switch rate, which, if we can get it to kind of stabilize and switch faster, will dramatically improve our temporal resolution and dramatically improve the number of traps we can do and improve the oscillation frequencies. But for now, it's kind of good enough to do some stuff. So the rest of my presentation and the rest of kind of what this experiment is all about is testing, now that we've built this thing, does it work like it's supposed to? Does it work like a continuous power trap? And to do that, the first thing we did was just gather some passive Brownian motion. Because if there's some interesting dynamics being induced by this trap switching, they should show up in one of the 3 conventional Brownian motion measurements. So in this case, we used 1 micron polystyrene spheres, and in fact, in all cases, we're using 1 micron polystyrene spheres, but because our in-situ calibration is robust to whatever particle you want, you could put in 2 microns, 5 microns, 0.1 microns, all of that would work in this system. We're using 1 microns because we have a lot of them. We placed 2 adjacent to one another. I believe it was at 5 micron separation, but there's no interesting hydrodynamic effects here. This is literally just to see, is their Brownian motion weird? I.e., are we switching fast enough such that their Brownian behavior approximates effectively a continuous power trap, or 2 continuous power traps? And to test this, we really just did the 3 common measures of Brownian motion. You do a Gaussian fit to the position histogram, you do a Lorentzian fit to the power spectrum, and an exponential fit to the autocorrelation of each of the trajectories. And what we found was, A, that all 3 of those fit rather well, even if there is a mild difference in the trap stiffnesses that you get out of them. And 2, one trap always ended up at lower stiffness than the other. And this is actually because our acousto-optic deflector has a differing diffraction efficiency depending on the angle. So the more it kind of deviates from the center value, the lower the trap power is going to be. And that makes validating some of the experiments really, really annoying, as we'll see a little bit later. But so far, the conclusion is nothing weird's happening, which is rather good, even though they don't have the same effective stiffness, but we can get around that using some interesting theoretical techniques for making predictions. So the next thing that we did was replicate a really old experiment from Maynard and Quake. Oh, technical difficulties there. The first thing that we do is replicate a passive hydrodynamic experiment. So this was just hydrodynamics of colloidal ensembles. We're going to start with 2 particles, and then we do 3 particles a little bit later. And this one's a really, really, really common experiment, or a really, really kind of conventional experiment from Maynard and Quake in 1999. Effectively, they put 2 particles next to each other and measured their hydrodynamic cross-correlation. So effectively, if you take the autocorrelation but replace one of the terms with the trajectory of the other particle. Now, we used 1 micron spheres, and we changed the separation a bunch of times. So we can see we have 3 different separations here. The values of the separations are just values that kind of matched our frequency scheme. There's no particular reason why it's 2.87, but that number rounds to a nice whole number in our digital frequency synthesizer. So that's why we've picked those numbers. And we found good agreement between theoretical predictions and the continuous power experiments. So the solid black lines are theoretical predictions that are actually an adapted form of Maynard's and Quake's equation, because Maynard's and Quake's equation assumes the two stiffnesses are the same. But again, you can check out our actual derivation / stealing of that equation in the conference paper. But one thing that we found, or the things that we found, were that there is a fairly good agreement between the hydrodynamic cross-correlation, we see this kind of anti-correlated behavior, and the theoretical predictions for our particular trap stiffnesses. It could be a bit better, but the correlations do kind of follow the shape you expect, and they do have the magnitudes and time constants that you expect. So this was judged a success, and we moved on to some more interesting experiments. One thing that I was particularly interested in doing is multi-colloidal hydrodynamics, and what we decided to do was we examined some simulated predictions for three-particle systems. So this top one is actually taken from this paper by Herrera-Verade et al. And this is effectively what happens when you take two particles and they've got a certain separation and they're hydrodynamically interacting, and you put a third one in there. What happens? How does the hydrodynamic interaction change? And so in their predictions, you've got the yellow curve, which is just the two-particle case. That's what this 2p here stands for. And the green curve is the three-particle case, so when you put the third one in the middle. And what they find is a reduced magnitude of anti-correlation and a reduced time constant of anti-correlation. And we find the same thing. So we've got our red case here, which is the two-particle case, and our blue case, which is the three-particle case. And so our experimental results show a similar qualitative behavior to their predicted cross-correlation. All of the data are kind of in normalized units in this paper, and ours are non-normalized units, so we just settled for a qualitative comparison. But this also kind of looks like what it's supposed to look like. So we move on to a couple of other experiments, which are more fun. The first one is two-particle active system. So what we did here is we took one particle, took a second particle. There's still 1 micron spheres. It's always 1 micron polystyrene spheres. Same trap power, all these different experiments. And we oscillated one of them. And the prediction here is based on Ho and Ouyang's paper in 2002, where effectively the one that's jiggling, the one that's oscillating, should have its response, which is effectively the magnitude of the sinusoid that it traces out, should start to decrease dramatically as it effectively lags behind the trap so much that the trap loops back around before it gets a chance to move. So this is effectively just plotting the sinusoidal response versus driving frequency of this sinusoidal oscillator. Now, one thing that's interesting and predicted and observed by Ho and Ouyang is that the second particle, even though it's just static adjacent to this sinusoidally oscillating particle, should be driven, and it should be driven in a resonance. So we should get, for some particular frequency, a non-negligible resonant sinusoidal response. And that's what we find. These two data points are data points for my data, and the black curves are theoretical predictions that are basically effectively Ho and Ouyang's theoretical predictions, with no fitting parameters, which I thought was pretty nice. So we're getting fairly close data to what is predicted. Then we decided to do something fun. We just put a second driving particle in there. So now we've got the middle particle. It's experiencing driving from one particle and a second particle. And because, again, our system can just take arbitrary position values, we put the two sinusoidal oscillators in phase, and then we put them out of phase just to see what happens. And it turns out when you put them in phase, you get a rather large response. This theoretical curve is just me multiplying the response by 2, because I guessed that it should be similar to twice as much. And it kind of is. It doesn't fit perfectly at the low frequency end, but that's fine. We didn't really do a big theoretical derivation for this. But interestingly, when it's out of phase, you get a flat line. There's nothing happening, which is really, really a good validation that our system is driving systems or driving particles in the way that it should, and can be used for really interesting hydrodynamic experiments. Just as a quick aside, don't have to do sinusoids. I did some step functions just to see what happens if you just rapidly step a particle in front of another particle. Does it push it around? These aren't really matching any theoretical curves. It's just an interesting point. But the conclusion is that our system kind of works, right? It allows for interesting and arbitrary configurations of trapped particles with photodiode-based position sensing. The experiments that we attempted produced really similar results to continuous power experiments and really similar results to theoretical predictions. So time sharing is a promising methodology for multifunction hydrodynamic investigations, right? One thing I want to emphasize is that all of the experiments in the theory that we've been talking about, or all the previous experiments were done with different hardware, and ours is just the same hardware. You just put in a different series of traps for the FPGA, and it will handle all the experiment. So please check out the proceedings paper, and I am just about over time, so thank you so much for having me here to present.